This tutorial will show you how to run a multiple regression in SPSS. And we are going to do this using the data set that is shown in the Andy field text. And in this data set, what we're trying to do is we're trying to predict album sales, and that's based on the variables of how much airplay there is, advertising, budget, and also the attractiveness of the band. So the first thing you want to do when you're going to run a multiple regression is you're going to go to Analyze, Regression, and Linear. And then once you're here, we're going to put our dependent variable, which is album sales, over here. And then we're going to go ahead, we're going to put all of our other variables in this block. As you know, there are a lot of different ways to enter variables into a regression. You can do stepwise, or if you have a theory, you can put them in a certain way. But because we don't have any specific theory on how these variables will predict album sales, we're just going to put them all in at once and say enter. So now we're going to go to statistics. And we don't need the R-squared change here. We only have one block, so we don't need that. But we do want our descriptives, our part and partials, our collinearity diagnostics, our Durbin-Watson. And so we're going to go ahead and look at all of those and hit continue. We're also going to go to our plots. And the reason we are going here is because we are actually going to put the z-scores of our residuals in, and we're going to compare them against the z-scores of our predicted scores. And the reason we're doing that is because we can look at testing different assumptions like independence of errors, homoscedasticity, and linearity. And we also want to produce all the partial plots because, again, that helps us look at the linear relationship between the variables. We're going to go ahead and look at normality as well. All right, and I think that we're good here. Hit OK. All right, so here the first thing you see is your descriptive statistics, regular mean and standard deviation, your sample size. Here are your correlations, and what you want to look at here is you want to look, this is a way of looking at multicollinearity, and you want to look for any correlations that are higher than 0.9. And as we look here, we don't see any correlations that are higher than that, so we don't have any issues of multicollinearity. You see here how we entered the variables. Okay, so here we have our R-square, and our R-square is our effect size, remember? So basically, this model predicts almost 67% of the variability in album sales, which is huge, and that's an enormous effect size. So that's exciting. We want our adjusted R-square to be very similar to our R-square, and it is. So that's good too. We look at our Durbin-Watson. And here we're looking at error variance, and we want it to be close to 2, and we see that it is very close to 2, so that's very exciting. We go down here, and this is the ANOVA that it ran. The ANOVA tests whether the model is significantly better at predicting the outcome than using the mean as a best guess, and we see that that is significant. And we also can see that our total model sum of squares here is very large, which is what we want. So now we're going to go down and we're going to look at our coefficients. The main thing you want to look at with your unstandardized coefficients are here. So basically what this tells you is that for every unit that advertising budget increases, album sales increase by 0.085. So not that much, but if you look, the real increase is actually down here with attractiveness of the band. And so it indicates that for every unit that attractiveness of the band goes up, additional album sales go up 11.086 units. So that's very large. We can go over here and look at our part and our partial correlation. The partial correlations represent the relationship between each predictor and the outcome variable, controlling for the effects of the other two predictors. And remember that the part or the semi-partial correlations represent the relationship between each predictor and the outcome while controlling for the effect of the other two variables. Then we're also going to want to look at our collinearity diagnostics, and we're going to see here that any VIF larger than 10 would be a concern, but we don't have anything like that, and we want to make sure that our tolerance is lower than 0.2 and 0.1, and so we're good there. Okay, so now we're going to go down and we're going to look at our plots. We see here that our residuals are normally distributed. That's exciting. You see that we got a linear relationship here. And this is good. What we want, this is our plot of our standardized predicted values and our standardized residuals that we wanted. And we want this to not look like there's any relationship. That's good. It means there's independence of error here. And then and you see here our partial plots, and these are scatter plots of the residuals of the outcome variable in each of the predictors. And so we want these to be linear. That's what we're looking for, a linear relationship, and we can also notice any outliers that we might have. But all of these look pretty good. And there you have it. So when we're trying to predict album sales, we'll go back up here and see that of our predictors, the one that it predicts the most is attractiveness of the band, followed by number of plays on the radio and advertising budget, and our overall model predicts a lot of the variance in album sales, almost 67%.